Chapter 13 is on reaction rates. So a lot of these, we'll get these started and we'll answer your questions as we go along too, so we get some of these here. But it basically depends on how fast reaction occurs with a given amount of materials. So if you, basically if you increase how much you have, increase the concentration, so what you start with, you increase your reaction rate because you have more collisions, more things to have to hit each other, the faster reaction is going to go. So increasing the concentration of the reactants will increase the concentration rate. Increasing the temperature will increase the reaction rate. So you can increase concentration and you can increase temperature. Right? Increase concentration, you have more of the stuff in the solution to hit for the reaction to occur. Increase the temperature, things hit with more force to be able to have the reaction occur. Okay, the more force they hit, the greater they'll overcome that activation energy we talked about, the more chance the reaction is going to occur. Okay. We talked about the enthalpy changes. Like if we had the equation HCl, we had hydrochloric acid plus OH minus, which is a base, is going to go to Cl minus plus H2O. Okay. The delta H for that reaction, okay, is negative 55.8 kilojoules. Whenever you see a negative delta H, you know the heat is on the right-hand side. So you talk about heat's being released. Positive delta H, heat's being absorbed by the reaction. So your activation curve, your activation energy is going to look like this. It's going to have a lower activation energy because it's the products. These are your products here. These are reactants. They're at a lower energy. Okay? So the reaction is going to occur releasing energy. That's a negative delta H. Okay? That's an exothermic reaction. Endothermic reactions would be the opposite. The curve would be like this. Your products would be up high, your reactants would be lower. That'd be a positive delta H. That takes energy to get up there because the products are at a higher energy than the reactants. And we've done energy diagrams. We did exothermic, endothermic before. So the reaction rate depends upon heat, temperature, okay, concentration, and the activation energy, how much energy it takes for these reactions to occur. Okay? So it's got to hit with enough force to overcome that hump of reaction rate. And now we're going to talk about a catalyst. Okay? A catalyst will not change the overall amount of reactants and products for equilibrium. What it will change is how fast the reaction gets there. So what a catalyst does is lowers the activation energy to make the reaction occur quicker. Okay? And it is regenerated in the process. So if we had an energy curve that looked like this, okay, if we added a catalyst, it will look like this. Your reactants and your products are the same energy. They're at the same point at equilibrium, but the activation energy is lower. So more collisions will have the energy for the reaction to occur. So the reaction is going to occur at a faster rate. Okay, it doesn't change the energy of the products and the reactants, but it occurs at a faster rate. And it is not used up in the reaction. That's the two things of catalyst. It allows the reaction to occur at a faster rate, okay, and it is not used up in the reaction. It's available for the reaction to keep going again. Okay. So we talked about energy diagrams, reactants and products. We did that. And catalysts. Perfect. Okay. Equilibrium is where the forward reaction equals reverse reaction. So like hydrofluoric acid goes to H plus F minus. When this rate, so that's rate 1, is equal to rate 2. Okay. That's at equilibrium. So there's no net change. When the forward reaction rate equals reverse reaction rate, there's no net change. That's equilibrium. Okay. So we got equilibrium diagrams. You can have, okay, if we had, let's show this diagram here. This is concentration, okay, and this is time. Okay. We start out with our products. Are going to start out at 0, right? Because we don't have any products left. With time, we start making product. Our reactants start out high, and reactants are used up with time as product is made. When these reaction rates are the same, we're at equilibrium. Okay? Equilibrium does not mean everything stops. It just means everything has had the same rate. The forward rate equals the reverse rate. So we're starting out with a high concentration of reactants and no products. And then as time goes on, we reduce our reactants and we increase our products. And everything has a different percentage of what's going to be converted. Okay. If you're going to produce a low energy product, you're going to have a lot of the product form. If it's a high energy product, there's going to be less product form. All depends how it's going to break down. And we'll be able to determine that by what's called our equilibrium constants. We'll be able to calculate a little bit here and show you how it does it. Okay. So basically, equilibrium favors the lower energy level. Okay? The lower the energy, the more stable the product is. Okay? Like I said, if you've got our reactants over time, if you've got this kind of a curve for your equilibrium, this is going to favor your products, low energy. This kind of curve is going to favor your reactants because the products are very high energy. Okay. 40 Bush reactions. Let's get an example here. We got that. We got that. That looks good. Okay. That's basically what they're trying to say for that section of the chapter. Okay. So if we had the reaction of acetic acid is a weak acid. Okay. So C6H5O8 with benzoic acid. Okay. Goes to H plus C6H5O minus. Okay. If we said that reaction is endothermic, endothermic means delta H is going to be a positive value. It's going to take energy. Okay. An endothermic reaction, would it favor the reactants or the products? So it takes energy to go, it's going to be, the reactant is going to be favored. So more at equilibrium, more of the reactant is going to be existent than the products. So this is going to be greater than 50% over here because this is an endothermic reaction. So if delta H or enthalpy is positive, it's going to favor your reactants. If delta H is negative, that's exothermic. That means your lower energy is in the products. So more products will be formed. Okay. And, okay. So now we've got our equilibrium expression. There will be some of these on the final exam. Equilibrium expression is K, and it could be EQ for equilibrium. K, the equilibrium constant, is equal to the products over the reactants, each raised to the stoichiometric equivalency. All that means is you're going to look at a balanced equation. You're going to put the products on top, reactants on the bottom, and the coefficients you use to balance the equation, you're going to raise the concentration of each one to that number. So if we had the equation AA plus BB goes to CC plus DD. Okay. The products are C and D. So those are your products. And reactants are A and B. And you're going to raise each to what this coefficient is when you balance the equation. Could be 1, 2, 3, whatever. But this is C raised to the C power, D D raised to the D power, A to the A, B to the B. That's all it is. And there's two things you have to remember specifically. Solids and pure liquids do not count. So if it's in a solid phase, you do not put it in the equilibrium expression. That becomes real important for solubility products. So solids do not enter into the equilibrium factor. And pure liquids like water liquid does not enter in the expression. Now, if water's in the gas phase, it will enter in the expression. But as a pure liquid, it will not, because that's what the media the reaction is occurring in. Okay. So if we had the equation, let's do an easy one at first. HCl goes to H plus Cl minus. This is aqueous, aqueous, aqueous. K equilibrium for this is going to be the products, H plus, over the reactants, Cl minus, divided by the reactants. Okay? And each one of those, the stoichiometric equivalency, the number in front of it is a 1, so it doesn't change it. So it's the concentration of H plus times the concentration of Cl minus divided by the concentration of hydrochloric acid. That's your equilibrium constant. Okay? If it's a strong acid, K equilibrium is very large. HCl is a strong acid. You're going to get very large K equilibrium. Okay? If you have a weak acid, like hydrofluoric acid, K equilibrium is going to be very small. With a large equilibrium constant, you have more product. Because the products are your top numbers, make your number bigger. With a very weak acid, most of it's going to be in the molecular form. So you're going to have a very low K equilibrium, because most of the product is going to be in the molecular form. Okay. Okay, so say we heat Br2. Let's do a couple examples here because I guarantee you'll see these on your final. Say we heat bromine goes to 2Br. What's the equilibrium expression for that? K equilibrium is going to be the products, Br, raised to this coefficient, 2, divided by concentration of Br2. So if you know both concentrations, you can tell the equilibrium constant. If you know the equilibrium constant in one concentration, you can tell the other one. All right, we making sense so far? I'll look for a thumbs up here. If not, I can go over to it. All right, perfect. You got it. All right, let's do an example where we have to actually use numbers. We can do some calculations here. It says nitrous acid ionizes in water, as shown in the equation below. At equilibrium, the concentrations are given. So nitric acid, HNO2, okay, dissolves to H plus. Wow, I didn't put the concentration brackets on there. Plus NO2 minus. Okay. So the K equilibrium, it says the H plus concentration is 0.0140. It says the NO2 minus concentration is 0.0140. And this is example 13.5 if you want to follow along with it. And it says the concentration of nitric acid is 0.493. These are numbers at equilibrium. And those are all molar concentrations. Okay. So K equilibrium, as that says, calculate the equilibrium constant for this reaction. Okay, concentration of your products, multiplication of the products, divided by the reactants. Okay, and each one raised up to the number used to balance it with, and each one of those is a 1. So you don't have any exponents for raising it to. So we have 0.0140, 0.0140 divided by 0.493. Okay, where's my calculator? All right, 0.0140 times 0.0140 divided by 0.493 equals 3.98 times 10 to the negative 4. Times 10 to the negative 4. That's your equilibrium constant. And with equilibrium constants, there's no units because they're all going to be different. One's going to be molars. This would be molarity. This would have to be molarity, but it could be molarity squared, molarity cubed. Okay, units don't mean anything with equilibrium constants. So there's no units. One of the few things in chemistry where there's no units. So the equilibrium constant is 3.194. So let's do another example. Okay. All right, write the equilibrium expression for okay. We got aluminum chloride plus Cl minus, and equilibrium expression is AlCl4, and all those are aqueous. Okay. So the equilibrium constant would be products over reactants each raised to the number that they balance the equation with. And that's it. That's your equilibrium expression. Okay. Now, that's okay. That should all make sense. It's nothing new. So let's do one like this. Let's do ammonia that we add into water. Okay. Goes to OH minus plus ammonium ion, NH4 plus. Okay. Everything's in the aqueous phase except water, which is in the liquid phase. Remember, if we have something in a pure liquid, okay, it does not get included in the equilibrium expression. So for this one, not in here. Go watch TV, guys. So equilibrium constant is equal to your products, which is OH minus NH4 plus, okay, divided by concentration of NH3. And that's it. You do not include water in your equilibrium expression. That is your solvent. Remember, solids and pure liquids are not included in the equilibrium expression. So let's do one that you do calculations again. Let's do example 13.7. Okay. Let's say hydrocyanic acid dissolves in water to produce H3O plus and Cn minus. So hydrocyanic acid dissolves in water to produce H3O plus Cn minus. Everything's aqueous except water, which is a liquid. And it says, determine the equilibrium constant for this reaction, or it gives you the equilibrium constant, I'm sorry. The equilibrium constant for this reaction is equal to 4.9 times 10 to the minus 10. So it gives you the equilibrium constant. And it says the equilibrium constant for this reaction, if water and cyanide are both equal, okay, the H3O plus and the cyanide are both equal at 7.3 times 10 to the minus 6, that's a 7. Both those are equal. Okay. What is the concentration of HCN in the solution? equilibrium constant is equal to H3O plus over Cn minus divided by concentration of HCN. And water does not come into equilibrium constant. It's a pure liquid. Okay, so we're looking for HCN. So we saw for HCN, concentration of HCN is equal to concentration of H3O plus times the concentration of Cn minus divided by, now what happened? Equilibrium constant. Okay, just rearranging that algebraically. And concentration of H0 plus, we said was 7.3 times 10 to the minus 6. Times 7.3 times 10 to the minus 6 divided by the equilibrium constant, which is 4.9 times 10 to the negative 10. All right, and we get our calculator. I think we learned how to do that last time on our calculators by using by turning it sideways. So turn it sideways and put in on the numbers you would key in be 7.3. You put EE. Okay. You put 6, and then to hit the plus minus sign, make it negative 6, and then times 7.3 EE 6 minus, then divide. You're dividing by 4.9, and then EE, and then 10, and then negative. Change it to negative 10. Okay, and that equals 0.109. That is constant, and that's in molarity. That's a concentration, that's not equilibrium constant. Okay, so 0.109 molarity should be your answer. Oh, they round up to, it's only 2 significant digits, sorry. It's supposed to be 2 significant digits, so that runs off to 0.11 when you do the correct non-significant digits molarity. Because you're only good to 2 significant digits. Sorry about that. All right. Any other? Let's see how we got with that. That looks good. That looks good. We said solids are not included in the equilibrium expression. So we can do solubility products also that way. So let's do one of the examples like that. Say you wanted to do the equilibrium expression for calcium hydroxide. Calcium hydroxide is a solid, dissolves in water to give you calcium ion plus OH. Okay. So this is called the KSP, the solubility. It's the same thing. The solubility product, the equilibrium constant, the partial pressure of gases, it's all the same equilibriums. Okay, so with products over reactants, so your products are Ca2 plus and OH negative, raised to the second power, because of this 2 right here. Okay, and divided by potassium hydroxide is a solid, so you don't include it. So just divide by 1, which doesn't change anything. So that's your equilibrium expression right here. At equilibrium, it's equal to the concentration of calcium times the calcium hydroxide squared. Okay. And those are what's called solubility products because a solid is dissolving. And you can get a list of those on in a chemical text. You get a list of equilibrium constants. The larger the equilibrium constant, like 1.8 times 10 to the 25th, the larger that number, the more it favors the products, the more products are going to be formed. The smaller the number, like 1.793 times 10 to the negative 18, that's a really small number. That favors the reactants. You have more of the reactants present than products. So the bigger the number, the more products. Smaller the number, the more reactants. Okay. So let's say we had manganese carbonate, manganese 2 carbonate. Let's do that one. It's example 13.8 in your book. So MnO2, manganese 2 carbonate is a solid. Okay, and it dissolves into manganese and carbonate. Okay, it says a saturated solution of manganese 2 carbonate at 25 degrees Celsius, both manganese 2 plus and carbonate 2 minus are equal, and they both equal 4.73. Times 10 to the minus 6. And they're both equal to that, right? 4.73 times 10 to the minus 6. Okay, and it wants to know what, write an equilibrium expression and calculate the value of the KSP for this constant. So the equilibrium, the solubility product is your equilibrium constant, just dealing with solubility of a solid. Okay, so KSP is equal to products over reactants. So your products are concentration of manganese 2 plus and the concentration of carbonate 2 minus. And that one's going to be, nope, no square nut, everything's all the same, just like that. And then the reactant is solid, so that's not including your equilibrium expression. So that's equal to 4.73 times 10 to the minus 6 times 4.73 times 10 to the negative 6. Okay. Let's do it the easy way this time. Let's just do it on our calculator, simple. 4.73 times 4.73 gives you 22. And how many silicon digits here? 3. 22.4 times 10 to the negative 12. Okay, just adding those exponents together that way. So it becomes 2.24, scientific notation. And I made that number smaller, made this number bigger, minus 11. 2.24 times 10 to the minus 11. All right. All that making sense? So far, so good, Tara? Does there have a question? You can put a question in chat and I can see it too. I got chat up there. If that's not making sense. Okay. I don't see any questions coming up. Perfect. Let's do one a little bit different with the math. Those are all equilibrium expressions. So 13.9, you solve the other way around. Okay. It says the solubility product of barium sulfate is 1.08 times 10 to the minus 10. If barium sulfate is dissolved in pure water, what is the concentration of barium ions? Okay. So let's write the expression, barium sulfate. That's a solid, breaks down into Ba2 plus SO4 2 minus. And you know the solubility product, KSP, is equal to 1.08 times 10 to the negative 10. Okay, and he wants to know the concentration of barium ions. So when you look at it, you have to realize the concentration of barium ions is going to be the same as the concentration of SO4. It's breaking down 1 to 1. So we got our KSP is equal to concentration of Ba2 plus times the concentration of SO4 2 minus. And those are equal. So we can say that's equal to our concentration squared. right? Just put an X for the value we want. Okay, because that times that, it's going to be a squared number. So X squared, what we're looking for, is equal to 1.08 times 10 to the negative 10. X equals the square root of 1.08 times 10 to the negative 10. So you take the square root of, yeah, I know you have to do this sideways calculator again to get your square root function. So 1.08 EE 10, and then change the sign, then hit your equals, and then hit square root sign. And it comes out to looks like 1.04. So the concentration of barium, which is also the concentration of sulfate, 1.04 times 10 to the 5, negative 5. Molar. Right? All right, perfect. All we did is just these odds, all we just took the square root of it. All right, so that is our equilibrium expression. When we do KSPs, we're starting with a solid. That's what it is in K equilibrium. Okay. All right, one of our questions here. Let me put this back on here. Okay. If we have 3 compounds, we have barium. Let me take a look at here. We have 3 compounds, barium sulfate with a KSP equal to 1.1 times 10 to the minus 10. We have lithium fluoride with a KSP equal to 3.8 times 10 to the negative 3. And we have nickel 2 hydroxide with a KSP equal to 2.0 times 10 to the negative 15. Okay? And it says the soluble products of the compound are shown. Which compound is most soluble? Remember, the most soluble is going to favor the products. Those are your ions. So which is most soluble? It would be the one with the highest KSP. That's the one that breaks down the most. So this would be the most soluble lithium fluoride. Which would be the least soluble? The least soluble is going to have the smallest KSP value. That's going to favor the reactants over your products, and that favors your solid. So lithium fluoride would have the highest solubility because it has the highest KSP. Nickel 2 hydroxide would have the lowest solubility because it has the smallest number for the KSP. All right. And one more thing here with this, I think. We got that, we got that. We can also use equilibrium products with gases in the same way. So let's take methane gas. React it with water, gas, goes to hydrogen in the gas phase plus carbon monoxide gas. Now let's write the equilibrium expression for this, and then we'll do some calculations, then we'll give some numbers. So the equilibrium expression is our K, or K equilibrium, is equal to our products, which is hydrogen. Oh, that's whoa. Okay, and then got pressure of hydrogen gas times the pressure of carbon monoxide gas. Okay, pressure of hydrogen gas is cubed because of this number right here. Okay. Divided by the pressure of methane gas times the pressure of H2O gas. Now, before you yell at me, water is included in this because water is in the gas phase and it exerts a pressure. If water was in the liquid phase, you would not include it. Remember, I said pure liquids and solids. Water is a pure liquid when it's in the liquid state. So when water is in the gas phase, it is included in the equilibrium expression. Okay, so if we had, partial pressure of carbon monoxide and CH, what is the partial pressure of carbon monoxide? Okay, so we have this, and we have the K equilibrium value here is equal to 1.5 times 10 to the negative 6 for this reaction. So we're given that. And it wants to know what is the equilibrium pressure of carbon monoxide. So we're looking for this, and we're given the partial pressure of CH4 is 1 atmosphere. So this is 1.0 atmospheres. The partial pressure of water is 1 atmosphere. Okay. And the partial pressure of hydrogen is 0.1 atmospheres. And we want to know the partial pressure of carbon monoxide. So let's rearrange our equation. Partial pressure. Carbon monoxide is equal to K value times the partial pressure of CH4 times the partial pressure of H2O divided by the partial pressure of H2 cubed. I think that's right? We just solve for the partial pressure of carbon monoxide, CH4, PH2, yeah. We just rearrange that, solving for partial pressure of carbon monoxide. So the K value is 1.5 times 10 to the minus 6. CH4 is 1 atmosphere. H2O is 1 atmosphere. And partial pressure of hydrogen is 0.1 atmosphere, and that's cubed. So we have 1.5 times 10 to the minus 6 divided by 0.1 cubed. Okay. That's 10 to the minus 3. So we bring that up. So it comes out to, you don't need a calculator here. The bottom number comes out to 10 to the minus 3. Okay, so that's 0.1. 0.1 is 10 minus 1. 3 times is 10 to the minus 3. So 1.5. We bring this up, change the sign. Minus 6 plus 3 is 10 to the negative 3 atmospheres. That's the partial pressure of carbon monoxide. Okay. We're using it the same way that everything's in partial pressure of gas instead of concentrations now. All right, H4 gas, we did that. Le Chatelier's principle. This is a great principle. We use this one a lot. And Le Chatelier's principle just says when something's at equilibrium, it wants to stay that way. That's it. It's good. If you change something, it's going to change back to get back to equilibrium because that's where it's stable at. So if we had the process of the Haven process, nitrogen plus hydrogen, all gas goes to 2NH3, all in the gas phase. Okay. So if I increase something, the equilibrium is going to decrease to get back to normal values. So if I increase the amount of nitrogen, the system's going to decrease it to get back to normal values. So it's going to shift the reaction this way. So if I increase nitrogen, I'm going to decrease the amount of hydrogen because I use it up, and I'm going to increase the amount of ammonia formed. If I decrease the amount of nitrogen, my reaction is going to go this way to make more nitrogen, to bring it back to normal levels. So my NH3 level is going to decrease, my H2 level is going to increase, or the partial pressures. All right. If I increase the amount of H2, I'm going to try to decrease it. I'm going to shift my reactions to the right so I can decrease that level. Okay. So my amount of N2 will decrease, my amount of NH3 will increase. If I, let's say decrease the amount of H2, I'm going to try to make more H2, so my reaction is going to go this way to fill back up to the equilibrium level where it was at. Okay. So if I decrease the amount of H2, I'm going to increase the amount of nitrogen, decrease the amount of NH3. Okay, and the other side. If I increase the amount of NH3, the reaction is going to go to the left to decrease it, get back to normal equilibrium values. So if I increase the amount of NH3, add NH3 to it, I'm going to increase my amount of H2 and increase the amount of N2. It's going to shift the reaction to the left. Ah, I didn't mean to do that. If I decrease the amount of NH3, what's going to happen? I'm going to try to increase it again to bring it back up to levels. And that means the reaction is going to go this way to increase the amount of NH3. So I'm going to decrease the amount of N2 because to use it up, and H2, and increase my amount of NH3. Okay. So it just has, whatever we do to the equation is going to have the effect to equalize the equation back to equilibrium. Now, some of the things you have to realize is if you're dealing with a gas, gases have a certain pressure. If everything's in the gas phase, if I increase the pressure, if I increase pressure, okay, I'm going to push the equation where there's the least number of moles to both on the side. In other words, the total number of moles on this side is 4, 3 hydrogen, 1 nitrogen. The total number of moles on this side is 2. If I increase the pressure, there's more moles on one side, so it's going to push it to the lower side. So if I increase the pressure of that reaction, I'm going to decrease my M2, decrease my H2, and increase my NH3. I'm going to push my reaction toward the least number of moles. Okay. What else do I have? The other thing we have to worry about is heat. If the reaction is exothermic, means heat is being generated. So delta H is negative, exothermic, which means heat. I'll put a big H right here. Oh, I can't put an H, that's hydrogen. Sorry. I'll use our triangle, that's heat. Delta is heat. Okay. So it's on the right-hand side of the equation. Because it's exothermic, heat's given off. Okay. If I increase heat, my reaction is going to try to decrease it. So it's going to push it in this direction to make less heat. So if I increase the heat of the reaction, I drive it to the left. I decrease my amount of NH3, and I increase my amount of H2 and N2. If I decrease the amount of heat, equilibrium is going to try to reinstate it by being higher. So it's going to draw my reaction to the right to increase, to make more heat, to bring it back up. So if I want to make more NH3, I decrease the heat. I don't increase it. Decreasing the heat drives your reaction to the right, decreases your amount of nitrogen and hydrogen, and increases your amount of NH3. Okay? If the reaction was endothermic, it'd be the exact opposite. If delta H was positive, means heat would be on the left side. It takes heat for the reaction to occur. So in this case, if I increase the heat, okay, I push the reaction this way to decrease the heat. And I make more NH3, less N2 and less H2. So all the Chatelain's principle says is when you make a change to a chemical reaction at equilibrium, it's going to shift to return it back to those normal changes. So if I decrease something, it's going to shift the reaction to one side or the other to restate those values. That's all the Chatelain's principle states. Okay, let's see. Let's do a couple examples in your book here. If we had the reaction of ethanol, ethanoic acid here, I'm sorry, C3CO2H, plus water, or plus methanol, goes to CH3, CO2, CH3, the ester, plus water. Okay, there's your reaction. And it said by adding water, so here's my water. If I add water, which way am I actually going to go? Is it going to shift it to the left or the right? You want to take a guess? Perfect. Exactly right. It's going to shift it to the left. So if I increase that, I have to decrease that change. What would be the effect of adding CHO3 to the mixture, methanol? So if I add methanol, what would be the effect? You already ahead of me. It would shift it to the right to decrease that change. That's all it says. That's exactly what it does. Okay, we did temperature, we did pressure, we did the gas, we did all that. Perfect. All right, end of chapter, what was this, 13? Okay, so let's go through those questions you had. And then someone else sent some questions you want me to do, we can put those on there, and then we'll be all set. Sounds good. So let me get rid of this and let's set the emails over here so I can see them. The one you had, the first one you had trouble with putting equilibrium expressions in there, that's got to be something with the program because you have it right. So what I'm looking at, it's the subscripts or something messing up with your subscripts on there because you did it right. So if you have trouble with that, let me know and I'll give you credit for that one. If you just have more trouble with that one, because you're doing that absolutely right. But the next one, it says you got wrong with the numbers. So let's do that for you. Let's figure that one out. Okay, so in a saturated aqueous solution, silver carbonate, the silver ion concentration is 2.5 to 2.4. Carbon ion concentration is that. Calculate solubility product. Okay. Let's put a reaction. Now there's silver carbonate. Goes to 2Ag plus CO3 2 minus. Okay. So your solubility product is what you're dealing with, right? And it says saturated solution is equal to concentration of Ag plus squared times the concentration of carbonate ion. Right? And it says the concentration of silver plus the silver ion concentration is 2.53 times 10 to the minus 4. . . 4 . squared times the concentration of carbonate, which is 1.27 times 10 to the minus 4. Okay, so solubility products, just multiply those together, right? So we have let's do it this way. 2.53 squared times 1.27 equals 8.13. 378 is right. 8.13 times 10 to the, and that was -8, and -4 is -12. So the equilibrium expression, the equilibrium constant should be 8.13 times 10 to the -12. Does that make sense, Tara? Keep track of all. Most solubility products, most soluble favorite product. Depends on the solubility product. A very high solubility product favors the products, the ions. A very low solubility product favors the reactant, which is a solid. This is a low number. 10 to the minus 12 is a very small number. So it favors the solid, it favors the reactants. Okay. If it was very high, it would be the opposite direction. Keeping track of all balanced equations. I'm not sure I know what that means. Oh, just yeah, okay, yeah. You got to balance equations because you definitely need these coefficients, these numbers, because that's what these are raised to. That's what gives you that squared value. And this one here is just when there's nothing in front of it, that's just a 1. So these are raised, that's raised to the first power, which doesn't change the value. Okay. So that would be that one. Let's do the other one for you here too, which we got. And it says at 25 degrees centigrade, an aqueous solution has an equilibrium constant of 0.00101 molar for generic cation A, and a 0.000505 molar for generic ion B. What is the equilibrium constant of the generic solid A2B? So again, keeping track of the balanced chemical equation. You have A2B. So when you dissolve it, it's going to go to 2A plus 1B minus. When that dissolves. So that's your solubility product. So you want to calculate the solubility product, KSP, that's a K, is equal to your A anion squared times your B anion. And it says the concentration of A is 0.00101. Come on, computer. 0.00101 is A, and that's squared, okay, times B, which is 0.00505. 0.000505. Okay, do the math. Where are we at? There it is. All right, 0.00101, 0.00101 squared times 0.00505. That equals 5.15 times 10 to the minus 9. Did I do that right? Let me check my math on that. 0.00101, right? 0.00101, 0.000505. It's easy to make mistakes on that point. 0.00101 squared. 0.0101 times 0.000505. 10 to the minus 10. Sorry, I didn't think that sounded right. 10 to the minus 10. Gotta watch my zeros when I use my calculator. Okay. So you just do your equation, balance your equation, write your solubility product. Okay, products over reactants. In this case, your reactant is a solid, so it doesn't count. It doesn't get expressed in equilibrium expression. Okay, then plug in your numbers and do the math. And then we should come out to about 5.15 times 10 to the minus 10. Make sense? Perfect. All right, you had another one here of solubility products. It said the reaction of water goes to hydrogen gas and oxygen gas. Proceeds at a certain temperature. This time water is a gas phase, hydrogen gas, and oxygen is the gas phase. They reach 0.015, 0.002, and 0.003 atmospheres respectively. What's the equilibrium constant? Cool. So we know the reaction is water balances as 2H2O, goes to H, hydrogen gas and oxygen gas. And we've got 2 hydrogen, that gives you 4. That gives you 2 oxygen, that's perfect. Okay, all those are in the gas phase. So, okay, the equilibrium constant is equal to the partial pressure of hydrogen squared times the partial pressure of oxygen divided by partial pressure H2O squared. And plug in our numbers. It says the pressure of water, H2O, is 0.015. .0150 atmospheres squared. And it says hydrogen is 0.00200. And oxygen is 0.00300. Let's do the math. We have got 0.00200 squared. Okay, times 0.003 divided by 0.015 divided by 0.015, squared, equals 5.33 times 10 to the negative 5. Let's see, 1, 2, 3, 4, 5, yeah. Okay. Does that make sense, Tara? See if that makes sense to you. Okay. We'll continue on. That's what I got. Okay, perfect. That's exactly what I got too. All right. We both got it. It's probably right. Okay. And the next one are functional groups with molecules. And it looks like you put everything in right. They just did that. But no, that's not right. That's not a ketone. Okay, let's start on the. Now, do you have the same picture I got? What you have up here for the drawings? I mean, do you see in the upper left-hand corner, do you see? See if you see the same thing I have on my screen here too. Or I'll just share this screen if I need to. Okay, perfect. Look at the top left then. Okay. The top left has a hydrogen and a double bond oxygen here. That's an aldehyde group. Okay. So this is H, carbon bonded oxygen, bind to R. R is just a hydrocarbon group. This is an aldehyde. The one below it, you have exactly right. That one's an alcohol. Has an R group attached to an OH. The third one down, that one's a ketone because there's two R groups on opposite sides. So you put ketone twice. The one on the top is an aldehyde where you only have a hydrogen. If you replace this hydrogen with a carbon group, then it would be a ketone. Carboxylic acid, you got right, COOH at the end. And an ether has an oxygen in between two carbons. That's an ether. The top right is an ester, which you're right. It has a COO like a carboxylic acid, except the H is now an R group. So you have an R group, the COO, and another R group. That's an ester. Okay. An amine. Amine has an N group inside of it with all single bonds to it. Okay, all carbon groups to an NH. So we have a carbon bonded to nitrogen. Say bonded to hydrogen, bonded to hydrogen. That's an amine group. Okay. Has nitrogen there. Aldehyde, just like the same as the top left. Same exact thing as the top left. That's an aldehyde. Okay. A halide has a halogen, chlorine, bromine, iodine, or fluorine on it, which are right there. And then amide, an ID ending means it has a carbon-oxygen double bond attached to the nitrogen, not just a carbon. It's called a carbonyl group. So we have a carbon-oxygen double bond attached to the nitrogen. That's an amide versus an amine. That's it. Otherwise, you got everything right except for that one on the top left. That's an aldehyde. Then it looks like you got a polymerization problem. Polymerization just means you're gonna group off a section and repeat that unit over and over and over again. So if it's that one just has to be a group there. And that's all the polymerization is. You take that one group and go over and over and over again. So you have CH, CCl, CH, or whatever group you want to put on there. This unit is N times. And that's what makes a polymer. Just take that unit and bond to it, do another bond, another bond, another bond, and that builds a polymer. So whatever the distinguishing characteristics of it are, that's what turns out to be. And then when you do with proteins, okay, the primary structure of a protein is the order of amino acids. So it's either glycine, leucine, alanine, and so on. The primary structure is the order of amino acids. What order those amino acids are put in. Okay? DNA goes to RNA, RNA goes to your ribosome. The ribosome reads that original DNA code and it matches it to put those amino acids in a specific order in the chain. So you get this long chain, every one of those dots is an amino acid. And you get a chain of amino acids being formed at the ribosomes. Okay? That's the primary structure. The secondary structure. There's two secondary structures. Okay? It's now that chain will start to form a shape. It will either take on the form of a alpha helix, okay, or beta pleated sheets. In other words, they'll line themselves in these long sheets like this as they start to form, or they'll start to coil into an alpha helix. One of those two. That's your secondary structure. Okay. Your tertiary structure. Tertiary structure is when these two start to fold upon each other and start to form a three-dimensional shape. So this is your three-dimensional shape. So your primary one is all the little amino acids in a row. Secondary is when they start to fold into an alpha helix or into a beta pleated sheet, one of the two. Okay. Then you got your overall shape of the single polypeptide unit, which is a three-dimensional shape. It'll start folding upon itself due to hydrogen bonds, due to sulfur, disulfide bridges, due to hydrophobic interactions. Things like that cause this thing to fold into a three-dimensional shape, which is the overall shape with single polypeptide chain. Now, more polypeptide chains join into this shape. So we add this, like the hemoglobin. The hemoglobin is 4 polypeptide chains, 2 A's and 2 B's. So now when you add more chains to it, you get your quaternary shape. And that's the difference. The overall macromolecule containing more than one polypeptide chain. So you have your primary structure, which is just a straight line, the amino acid is sequence. Secondary structure is when they start to fold into one shape, either beta pleated sheet or alpha helix. Tertiary structure is the three-dimensional shape it takes on through disulfide bridges, hydrogen bonding, and it forms into a three-dimensional shape. When more of these units come together to form the final molecule, that's your quaternary structure. Does that make sense? Yeah, the wording is confusing, but it's just one step to the next, to the next, to the next. Okay. Yeah, their wording can be confusing. But what I explained, does that make sense to you? So where does the amino acids don't go anywhere? The amino acids stay in this, they form this long chain. So it just links amino acids together in a long chain, 50, 100, 1,000 for peptide. And then this chain starts to fold. It'll fold into one of two structures. It'll form into beta pleated sheets, okay, where they form these little peaks and valleys, or it'll just fold upon itself, making a helix, which is like a spring. Okay. It's like once like I'm trying to think how the best way. Take one side of a ladder and just start to bend it and fold it. Double helix would have both sides, but just take one side and fold it, and it would form an arch around it. And then it forms its three-dimensional structures because of like hydrogen bonding or sulfur bonding or disulfide bridges or hydrophobic interactions. Things like that cause it to make a three-dimensional shape. So single peptide is primary. Okay. Yes. A primary structure is just the amino acid chain. That's it. Just the list of the chain as it occurs. That's your primary structure. Then the secondary structure is how that one thing folds. Which one is tertiary? Tertiary is when this helix or pleated sheet folds upon itself to form a three-dimensional structure. In other words, so these coils start to form the structure like that. It's not a straight coil anymore. And you have hydrogen bonding that pulls these in, or you have little pockets here where there's hydrophobic interactions, and it forms a certain shape. Okay, that's tertiary. So the list is containing more than one polypeptide. What do you mean the list? The only time you have more than one polypeptide is the quaternary structure, where you have these shapes come together to form a molecule. Quaternary, right. Quaternary structure is when more than one of the tertiary structures come together to form the completed molecule. Like hemoglobin. Hemoglobin has 4 of these units that have to come together to form a functional hemoglobin unit. So these tertiary forms come together and they form a quaternary structure. So everything's one polypeptide chain until the quaternary structure. Then they come together and form the functional molecule that way. It's over program. It can be confusing. That it can be. But does it, the primary, secondary, tertiary, and quaternary make sense of what you have to move into each box? So the primary one, you would move in order of amino acids. Secondary structure would be your alpha helix or beta pleated sheets as your structure. Your tertiary would be the overall shape, okay, of a single polypeptide, a single line of them. Polypeptides is a protein chain. And then the quaternary would be more than one polypeptide that comes together. To form the functional molecule. Okay, so the order of amino acids goes alpha helix, beta pleated sheets, overall shape, and then the overall shapes come together with different polypeptides to form the functional molecule. Is that making more sense? More questions on that? Right. Yeah, the wording changes between, and it can be confusing. But hopefully this helps straighten out a little bit. Oh, no problem. Perfect. All right, I got one more person that wanted me to do some questions, and she's gonna watch it later. So let me click on these, and you're free to watch these, and I'll go through these with you. But kind of review what we did today with everything. So they have the equation A plus B goes to 2C plus D, are all in the gas phase. And it wants to express it using molar concentrations. Okay, so K equilibrium is equal to concentration of C squared. That's where this 2 comes from. Everything else was just 1, right? 2CD. Okay. Times the concentration of D, divide the concentration of our reactants. Products over reactants. Each raised to their stoichiometric configuration. Each raised to the number of the use balance equation. Okay. So that would be the KC. That would be the equilibrium expression that they want. Okay. Next one says write the equilibrium expression for the reaction shown. Okay. So the next one is 2NO. Nitrogen monoxide plus oxygen goes to nitrogen dioxide. Okay, and this is a 2, and that's a 2. And that's 1 from the oxygen. So the equilibrium expression would be product, which is NO2, squared over your reactants. NO squared and oxygen. Now these 2's are coming from right here. That's where we're getting those from. And that's your equilibrium expression. And this is when we did, looks real similar, just change the numbers a little bit. But let's do this, work this through this one. And it was a reaction of H2O goes to hydrogen plus oxygen. Okay, those are all in the gas phase. Okay, and to balance it is 2 hydrogens, 2 waters, 4, and 2. Perfect. So the equilibrium expression is equal to, and this is in pressures. So it's the products, so it's the partial pressure of hydrogen squared, partial pressure of oxygen divided by partial pressure of H2O. Remember, H2O gets included because it's in the gas phase. If it was in the liquid phase, we would not include it. And they put the values in. It says pressures of hot water to reach temperature and respectively. So it says water is 0.0100. So water is 0.0100 squared. Okay, and it says hydrogen is 0.00550 squared. And oxygen is 0.00300. Okay. Check my number, 0.05500 and 0.01. All right. So let's hit our calculators. And 0.0055 squared times 0.003 divided by 0.01 squared equals 9.08 times 10 to the, let's see what we got here. 1, 2, 10 to the 4, negative 4, 1, 2, 3, 10 to the negative 4. 9.08 times 10 to the negative 4 should be the equilibrium constant. Okay. I think you got 9.08 times 10 to the negative 2. That's probably because you forgot this square right here. That's probably the only thing you did wrong. And then OH values from a pH, and that should do it. Okay, let's review some more pH values. So it says calculate the OH on the pH associated with an H plus. So your H plus concentration is equal to 5.4 times 10 to the negative 7 molar. Okay, and you want to calculate the OH. So you know the H times the OH is always equal to 10 to the minus 14. So our OH minus is going to equal 10 to the minus 14 divided by 5.4 times 10 to the minus 7. Because those two always have to equal 10 to the minus 14 in the aqueous solution. So the OH value is going to be, so you hit 1 EE 14 negative, and then change sign to negative, and divide by 5.4 EE, change it out to negative 7, equals 1.85. That's a 5. Times 10 to the negative, and we got our numbers. 8. Looks like 10 to the negative 8. So we'll check that. 8. Yep. There's your OH and your pH for that. pH is just minus the log of the H plus concentration, which is 5.4 times 10 to the minus 7. So for that, we would go back to our scientific calculator, and we hit, clear that, that's 0. Okay, 5.4. Turn to negative 7. EE, 7 negative, equals that. And then take your log. And then take the negative of that, comes out to 6.27 is your pH. Okay. If you have any questions about chart, let me know too when we're doing this. This should be a good review for you though. Okay, let's do the next one. And the next one says OH, same thing, H plus. Isn't that what we just did? Wait a minute. 5.4 times 10 to the minus 7. Yeah. 5.4 times 10 to the minus 7, P and H plus. Oh, the next one is calculate the H plus and the pH of an OH minus solution. It says OH minus is equal to 7.5 times 10 to the minus 9 molar. And it wants the H plus and the OH. So H plus, it's H plus and the pH is equal to 10 to the minus 14 divided by 7.5 times 10 to the minus 9. Because remember, the H plus times OH has to equal 10 to the minus 14. So again, let's take our calculators, clear that. And we take 10 to the minus 14, so 1 EE 14, change the sign to negative, and then divide it by 7.5 times 10 to the minus 9, so EE 9 negative equals 1.33 times 10 to the minus, what is that? Looks like 6. Yep, 10 to the minus 6. That's your H plus. Then your pH would be minus the log of your H plus concentration. So from the calculator, you put 1.33 EE negative 6. And then you hit equals. That's the only difference. You have to hit equals first. Then you hit your log. Then take the negative of it. And it's 6.48.
What time do you get there?
A little bit.
Like what's a little bit?
5 minutes, 10 minutes. 6.48 would be the answer. And then there's one more problem, and that's it. That was listed on this email, and it's the H plus and OH solution. Now it goes to this the opposite. It gives you the pH. It has pH equals 7.51. and you want to know the H and the OH. So remember, minus the log of the H plus concentration equals 7.51. So the log of H plus equals negative 7.51. Okay. So did you inverse? You take 7.51, change it to a negative, and you hit 10 to the x. Okay? That's the inverse of the log. So when you see this sign, 10 to the x, that's the inverse of log. And that equals 3.09. 3.09 times 10 to the, and it's, looks like 10 to the negative 8. I'm trying to put in question 13. Question 1310, other people had trouble with it too. Someone sent me an email on that also. Just send me an email with your answer to it, and I'll give you credit for it. There's something wrong on the website on question 10 on homework 13. Other people had said the exact same thing. So just send me an email, and I'll give you credit for that question. Yeah, we'll cover 14, 15 next week, and then 16 on, are we going to run out of time? When's the final? The final, is the final the end of next week? If it is, I'll cover 14, 15, and 16 then. We'll cover all that next week. Yeah. Then I'll do that too here. So let's finish this one. This is the H concentration. And the OH is 10 to the minus 14 divided by that. And then I'll look at the polypeptide, the other one for the polymer. So 3.09, so 10 to the minus 14 divided by 3.09 times 10 to the negative 8 equals 3.24 times 10 to the negative, I think it's 7, let's see. Yeah. So, perfect. So that takes care of those questions. That's your OH, that's your H. And let me go back to your email, Tara. It's Thursday the 29th. Yeah, I think that's the last, and today's the 20th, so you'll have to look at it. But I'll make sure and cover 14, 15, and 16 next week. We just do 2 in one day. And okay, let me go back to your email. Has the formula. Okay. There's no question on the email. It just shows the formula for it. But it has CH3, C double bonded O, O, and then C, H, CH2. And this unit gets repeated a number of times. What does the question say? Draw the monomer. Okay, so this is your unit that repeats. So the monomer is the single unit. So the monomer you would draw, this is your monomer, CH3, COO, oxygen, bonded to CH, bonded to CH, and this would have a hydrogen here, and this would have a hydrogen here. So those would be hydrogens at those places. That would be the monomer. And you're just removing these hydrogens when you form the bond. So this is the monomer right here. Monomer is just a single unit. Polymer is that unit over and over and over and over again being repeated.